Good morning and welcome to everyone joining us for today's episode of AP Calculus BC Live. Thanks to viewers like you, this is now the #1 rated BC Calculus review show on YouTube Live at the 9 a.m. time slot, hosted by two Indiana teachers named Brian and Tony. So we certainly thank you for your support. Not only do we have a great show for you today, we have a really awesome week ahead as we start our Connecting AB to BC series of lessons. So we'll talk about that, what that entails as we move through the video. But basically you're going to see, obviously, limits and continuity as the core structure of our lessons today. Those are AB topics. And then these free response questions that we talk about will sort of segue into these larger topics in AB and BC that might be partially scaffolded by those limits and continuity topics. So we're really excited about that. As always, you have the ability to download any of the materials that you will want to use for any of our lessons in the description below the video, and you can certainly do that. You have time to take care of that now, print that out, and you can certainly follow along with us, and we would really appreciate that. I know your teachers would as well. Once again, my name's Tony Record, teacher from Avon High School in Avon, Indiana, and I'm joined by my wonderful, awesome friend, Mr. Brian Passwater, a teacher at Speedway High School. So Brian, you last night showed me a very cool math trick. Any chance that you could share that with us today? Put you on the spot.
Ooh, yeah, I think we might have some time for that, Tony. Maybe we'll use that as a teaser today. So maybe about halfway through our lesson, we'll take a quick brain break, and I will show you the same math trick I showed Tony last night, which was, I think, according to you, it was the quote, life-changing.
It did.
Yeah, it said it raised your coolness factor by a level of 12. That's pretty high for one math trick. So if you want to see a really fun, cool math trick that will amaze all of your friends and family and raise your coolness factor, stick around. And in about a half an hour or so, I will show you this. I lost my camera there, Tony. In a half an hour, I will show it to you. Sound good?
Sounds great. Sounds great.
Awesome. So before we get to that, how about we jump into some problems today? And then at the end of the lesson, Tony will wrap us up and show us what we're doing next week and kind of where we're going from here. So we are going to be looking today, like Tony mentioned, at limits and continuity. And of course, my screen wanted to share the wrong thing. So this is, I think, Tony, this might be our first major technical issue on the screen, and it had to be, of course, me that did it because, like I mentioned last week, you are much more tech savvy than I am, and so for me, if there's one of us that was going to mess this up, you knew it was going to be me. So there we go. How about that? Hopefully we're sharing the right screen now instead of that screenshot that I had earlier. Tony mentioned we are doing limits and continuity, and so we're going to go through a couple of quick checks before we jump into these free response problems that Tony mentioned. And the first one is a little activity that I made, and maybe you've seen it before. This is all new problems, but it comes from an activity I shared with some calculus teachers a while back called odd limit out. And how it works is you have different problems, and each problem has 3 statements, and then you would find the answers to all 3 statements. And if you did it correctly, 2 of the statements will have the same answer, and then one of them will be a different answer, and that's the odd one out, and that's what your answer is going to be. And so if you do these problems and you get 3 different answers for the 3 statements, you know you made a mistake. If all 3 answers are the same, you obviously made a mistake, but hopefully you'll get 2 of the answers that are the same and 1 answer that's different. And so we're going to actually start on problem number 2 here. I'm going to skip problem number 1, and we're going to jump into problem number 2. And so you're going to be able to go back and do problem number 1 if you would like to get a little bit more practice once we're done with this. So statement number 1 says, find the limit as x approaches 2 from the right of h of x. Remember, the little plus sign means from the right, and we're given a graph of h. And so the limit as x approaches 2. Remember, a limit just means, what if you were on the graph of h and you are approaching an x value of 2? And the plus sign means we're on the right side of 2. So we're somewhere over here. I'll put a little blue dot there on the screen, and we're going toward the value of x approaches 2. And we'll notice, wait a minute, there's a hole in the graph there, and there's some kind of weird jump, right? The other part of the graph jumps up here. A lot of weird things are happening there. This is the whole reason why limits are so valuable, because we're not able to plug 2 into the function because it would be undefined, but yet we can evaluate limits, especially from different directions. And so h approaches, or x approaches 2 from the right just means we're on the graph of h, we're getting closer and closer and closer to the point where x is 2. And a limit, remember, means where are you headed? So don't be fooled if there's a jump on that side or there's a hole or a random point somewhere else. A limit is simply asking if you're on the graph and you're going toward that x value, where do you think you're going? Where does it appear you're headed? Well, we're clearly headed toward this hole in the graph, right? And so a limit doesn't need a point to have an answer. It just needs to have a clear direction of where you're going. And so in this case, we're heading toward that hole, and the y value at that hole in the graph would be at 0. So that's our limit from the right-hand side. And then the second statement is the limit as x approaches 2 again. And if you can't see it, there's a little minus sign there, meaning from the left-hand side. So we're still on the graph of h. We're still approaching 2. But now we're going to start from the left-hand side of 2. I'll do this one in red. And we're still approaching 2, but from the left-hand side. Well, in this case, starting on the left, we're now approaching this hole in the graph. And that hole in the graph has a y-coordinate of 2. So notice neither one of those had a point on the graph, but we're not concerned about that. We're just concerned about where we think we're heading from the left and from the right. And then the third statement is going to be, what's the limit as x approaches -2? We don't see a left or a right, we just see the -2, which means in order for this limit to exist, we have to have the same answer from the left side as we do from the right side. And so if we're approaching -2, the x value from the left and from the right, those two segments in green are in fact approaching the same value, and they're both approaching this point right here, which happens to also be at 0. And so for problem number 2, we got answers of 0, 2, and 0. The good news is 2 of them did match, right? We got 0 for 2 of them, and then one of them was different, and that's going to be our odd limit out. So for problem number 2, the odd limit out is just going to be that answer of 2, because that was the one that was different than the other 2. Let's try one more here, problem number 3. Now we're going to take the limit as x approaches 3. And just like before, there is no left and right side to this problem. It just says 3. So we have to make sure that as we approach 3, we're coming from both directions. And now we have something a little bit different, right? We still have the same hole, which doesn't really make us too nervous, but we have this random point kind of placed above here, right? And so this is where it's important to know the difference between limits and then function values, and then tying those together later will be the idea of continuity. But if we're approaching x equals 3 from the left and from the right, remember we said it only depends on where you think or where it appears that you're heading. And so if I'm following along this path from both directions, both of these directions are going toward this location, right? This is where they're heading. And so since they're both heading toward that same location, this little hole is going to be our limit value. That's where we appear to be headed. In this case, that's going to be at a value of 1. So we're able to ignore that point because the limit is just where the graph appears to be heading, not where the actual point is, if there is one. And then the second one, h approaches 6 of h of x, again, from both directions. So coming from the left-hand side, as we approach 6, we're going this direction. This little dotted line indicates this is a vertical asymptote. And then coming from the other side of 6, we're approaching this way. And so this really brings up two interesting points. Number one, these are unbounded, right? They're going up to infinity or down to negative infinity. If a limit is unbounded, it's going to infinity. Sometimes you can write infinity down, but that's also an example of a limit that does not exist. In this case, though, these two limits are actually approaching different infinities. They're not even approaching the same infinities. They're going different directions, right? If your limit from the left and the limit from the right are approaching different directions or different values, that's one example of why a limit does not exist. And so we would say the limit as x approaches 6 does not exist. And then looking at the third one, x approaches -1. Again, we have to approach it from both directions because it doesn't tell us just a one-sided. And so as we approach -1 here from the left, we're going to be approaching along this path. And if we approach -1 from the right, we're approaching along this path. And notice from the left-hand side, we're approaching 2. But from the right-hand side, we're approaching -1. And so now, again, another example where from different directions, we're approaching different values. And in order for a limit to exist, we need that left-handed limit and that right-handed limit to approach the same answer. So this is another example of a limit that does not exist. So for problem 3, we had 2 answers that did not exist, and then one of them had a value of 1. So our answer there is going to be simply 1 is the odd limit out. So That's a couple of graphical examples of how we approach limits. And now we're going to connect this idea of limits and points to continuity. And so continuity is a step higher. So in order for a function to be continuous at a given x value, we have to have three conditions met. Number one, the limit as x approaches c from the left has to equal the limit as x approaches c from the right. This is a fancy way of just saying the limit as x approaches c of f of x exists, right? That there is a limit. It's kind of the equivalent idea of saying that. And some of your textbooks will just say that. What I found with my students, when I used to tell them the first step is show the limit exists, when they're given a piecewise function, they don't necessarily remember or think, oh, I have to check the left and right limit for a limit to exist. And so I think Tony and I are pretty similar in the fact that we automatically just tell our kids to check the limit from the left equals the limit from the right, because that's synonymous with saying the limit exists. And it tells you, oh, I got to do two things here. But not only can the limit exist, not only do we have to approach the same value, we have to make sure there's actually a point on a graph, right? There can't just be a random hole there. There has to be a point on the graph, so the function has to exist. And then finally, not only do we have to have a limit, and not only do we have to have a point, we have to also make sure that the limit and the point have the same value. So we don't have a hole on the graph with a random point somewhere else. So all three of these things have to happen in order for us to show that a function is continuous. If any of these three things fail, then the function is not going to be continuous at that point. And so we're going to look at a couple of examples of this. And on the bottom here, we have the reference to kind of remind you. And these are going to be really important for free response questions. So here's kind of like your AP exam tip number one of the day. You know, when we're doing free response questions, a big part of the exam is how you communicate, how you use theorems and definitions, and how you use notation. All those little things that students kind of overlook sometimes. We're so used to, at least my kids are, thinking the answer is what's most important. How do I get to the final answer, right? I might do some work on the side. That's for my own benefit as a student, kind of some scratch work. But here's my answer. Here's where you should look. Whereas the AP exam really is you telling a story, right? Each problem is you telling a story. And so you're trying to communicate to us what you were thinking every step of the way. And so it's really the burden is on you as a student to communicate. We don't get to guess what's inside of your head, what you knew and didn't know. If you don't put it down, we can't give you credit for it. So make sure that you show the proper steps. And then number two, show that notation. A lot of times students will look at the three steps and kind of know what it wants you to do, but then you won't use the proper notation, and that's going to end up costing you at least full credit. So maybe you won't get all the points on a problem that otherwise you really did understand and know how to do. And so continuity is a really good example of that, where we see a lot of students that clearly from their work understand what continuity is, but yet their notation and their communication was either lacking or missing, which results in them not getting full points. And so it's always sad when we see that, but hopefully from today, you will be reminded, or it'll reinforce exactly what you need to show on the exam, so that way you get all of those points that you deserve. And so here we're going to try a quick definition of continuity question. So part A, we have three functions, f, g, and h. Is f continuous at x equals 2, and give a reason for your answer? Well, if we're going to check for continuity, when a question asks us for continuity, that's when we know we're going to check these three steps. And so I always like to label them. Step number one, we have to show the limit from the left equals the limit from the right. And so we're just going to work that out. We're going to say the limit as x approaches 2 from the left of f of x, and then we're going to show the limit as x approaches 2 from the right of f of x, and we're going to hope that they end up giving us the same value. And so the limit as x approaches 2 from the left, we're going to use this top equation here, because this is for values that are less than or equal to 2, or the left-hand side of 2. And so when we're doing this, it's just good communication to not just put your answer, but to give some kind of evidence that you knew which equation to plug it into. And so we're going to go ahead and show that the limit from the left is going to be 3 times 2 minus 5, which is 1. So notice I didn't just put down 1. I showed this kind of intermediate step of me plugging 2 into that top equation. And the limit as x approaches 2 from the right is going to be cosine of 2 pi, if we plug in 2 for x here. And then cosine of 2 pi on the unit circle is also going to be 1. So notice our first requirement is met. the limit from the left did in fact equal the limit from the right. And then we're going to go to the second requirement, which is, does the point exist, right? Just because the graph has the same limit, it means they're heading toward the same place, but can we guarantee there's a point on the graph? Well, if to do that, we would have to check f of 2 in this case. And can we plug in 2 into either of those problems? Well, this equal sign here on the top tells me, yep, we can plug in 2 into the top equation, right? Because it has the equal sign. And so f of 2 is just going to be plugging in 2 to the top, which happens to be 1. We've already found that. And so now the third step is to show that those values are the same. Well, we can clearly see we had the same answers for each of those. And so now for our third step, we can just verify, hey, guess what? The limit as x approaches 2 from the left of f equals the limit as x approaches 2 from the right of f, which happened to equal f of 2, right? Notice how I plugged in 2. And then I think one of the big things that Tony and I see is that it's really tragic is students will do part 1 and part 2 beautifully, and they'll get to part 3 and they'll have the right idea. But you know what we see a lot of students doing? They forget to put the f of f there, right? You're never allowed in math to write a limit with a number there equals something, right? There has to be something next to the limit, an argument, right? There has to be an argument there. Putting limit equals something is equivalent to kind of saying square root equals. Like you have to have something inside of the square root. You have to have an argument, something you're taking the square root of. Same thing with limit. So never in your life should you see an LIM equals LIM without the function being named. That would be all this beautiful work and then one bad notational error, which means it's going to probably prevent you from getting the full credit on that question. So we were able to check all 3 of those pieces. They were all true. So since they were all true, we can reach our conclusion and we can say, yes, f of x is continuous at x equals 2. And if I have all my work clearly laid out like this, that's all we have to say. This is our reasoning, is our work. This is our justification by saying all those things. So let's look at one more. I want to skip part B and go straight to part C of this because it's looking at it a little bit differently, which is we're now looking at the function g, and we're going to ask not is g continuous, but find the value of k that makes it continuous. So we're still using our idea of continuity, and the real idea here is if g is going to be continuous at 3, that means the limit as x approaches 3 from the left is going to have to equal the limit as x approaches 3 from the right. That's the only way for a function to be continuous is that first step has to be true. Well, if I take the limit as x approaches 3 from the left, I'm getting this top piece here. I'm plugging 3 in for x, right? Not for k, but just for x. So from the left, we're going to get 9k minus 6 if I plug in 3 for x's. And that should equal the limit as x approaches 3 from the right, meaning I'm going to plug in 3 to the bottom, which is going to be 6 plus 3k. Now we have a nice little equation for k. We can solve this pretty easily by putting the k's on the same side and making it equal 12. And then we're going to get k equals 2. Now we can quickly verify the other answers are going to be true, that we do have a point because we can plug in 3 into the bottom. And if we checked all of these left, right limits and the function value, they would in fact be the same. We don't have to check all 3 of these because the question wasn't to see if it's continuous. It just wants me to find this value of k, which means I know the left and right limit are going to have to be the same. So that's quick check number 2. And then on quick check number 3, we're just going to look at one really quick problem just so you can see a combination. We started off with a graph, then we went to a piecewise function, and now we're going to mix it up a little bit where we have a graph and a piecewise function. And so quick check 3 part B says, is the function k, now notice k is the middle one, right? I'm on B if you're following along. We skipped A. Is k continuous at 2? Well, our first requirement, remember, if you from that previous slide, is that the limit as x approaches 2 from the left needs to equal the limit as x approaches 2 from the right. And so if we go ahead and find these 2 values, the limit as x approaches 2 from the left is going to use this top function. So we're approaching 2 from the left of the graph of m. Well, here's the graph of m. I have to approach 2, but from the left-hand side. So here's when x is 2, but coming from the left, we can see we're following this path, and we're going to be approaching this hole in the graph, which is at 2. And then if we're going to approach 2 from the right-hand side, we're now following the graph of p of x from the right-hand side. So here's the graph of p. We're still going to be approaching 2, but now we're coming from the right-hand side, and we're going to be approaching this value right here, which is simply 1. And right off the bat, we can see the limit from the left does not equal the limit from the right. And so we can stop. If all 3 conditions aren't met, we're done. And so is k continuous at 2? No, k of x is not continuous at x equals 2. And then all we have to do is kind of mention which one of those 3 rules were broken. Well, which one was broken? The limit from the left, x approaches 2 from the left of k of x, did not equal the limit as x approaches 2 from the right of k of x. And so notice all of the notation and work that we showed on proving that things are continuous. Continuity is a really good problem that I could definitely see the exam putting on this year's test with this new free response style, because it tests a lot of things, but also it shows you the need to communicate clearly. So those are going to be our quick checks. There is a quick check 4 in the notes or in the materials. We're not going to look at quick check 4. These are advanced limits. And I will tell you on a normal year, you might see one of these problems on a multiple choice question. The chances of it being on free response is virtually 0. They're very, very challenging. And so if you want to try quick check 4 on your own, there's lots of really tough ones on there. And you see the answer key, you're going to be maybe thinking you got all those wrong, possibly. Don't panic. If you can't do quick check number 4, it's probably not going to be tested this year. So that's why we're going to skip it for right now, but it's there for teachers. They can use it next year, but don't worry too much about quick check number 4. So now Tony is going to transition us now to going from these quick checks to these free response problems that are going to be connecting A, B to B, C. So Tony, what do you got for us?
Certainly, we're going to dive in here to BC1, and it reads, the graph of the twice differentiable function f is to the right in the figure, or above in your particular handout, for the interval -3 to 6. The area is bounded by the graph of f of x, and the x-axis are labeled in the figure. And it's also known that f has relative extrema at x equal -1 and x equal 2. The function g is not explicitly known, but g prime, the derivative of g, is defined by the piecewise function that you see there. G prime is f of x from -3 to 0, and g prime is x times f prime of x from 0 to 6. So certainly a lot's going on in terms of the stem and what information is being provided. But the question is a familiar friend. Is g prime continuous at x equals 0? Give a reason for your answer. So we're going to go ahead and organize this in a very similar fashion. Now, we don't have our little reference there in the corner. So if you have to flip back to the definition of continuity to point, that's certainly okay. If you think that you can kind of memorize it and put it together as we move along, that's all even better. So the function g prime is what our focus is. So we're going to go ahead and attack it from the one-sided limit standpoint. That's the way that we always want to deal with piecewise functions with continuity. So we think about, well, what is this limit of g prime as x approaches 0 from the left? Well, g prime can be 2 different things, right? 2 different definitions. But as we are on the left side of 0, right, that means that we're going to be looking at the top piece. So basically, taking the limit of g prime is every bit the same as taking the limit of f. Well, what can we do about that? Well, you'll notice that the stem of the problem mentions something about twice differentiability here for this function of f, which implies that f and his derivatives are going to be continuous. So that does give us the ability to sort of evaluate this function specifically at that 0. It's something I refer to as a green light in my classroom. So we can actually fill in that x with 0 because of that continuity of just the f of x by itself. And then we look at this f of 0 and we think about, well, what are we going to do about that? And we see the function f appear very nicely displayed, and we see that the y value there is certainly equal to 0 when x is approaching 0. So that takes care of the left-sided limit. Let's do the same thing for the right side, shall we? So we have the limit as x approaches 0 from the right of our g prime. This time g prime takes on a little bit of a different look. As we are moving towards 0 from the right, that's the same as being larger than 0, we find that we want to use the definition denoted by x times f prime. So we'll slip that in place of the G prime. And again, we have a situation where individually, these two pieces are continuous. So we would be allowed to invoke some limit properties. We can bust them apart, use two separate limits. So the limit of a product is the product of the two limits. Or we could just really quickly see that on the fly, and we could directly substitute 0 in for x, which works fine. We could go ahead and substitute the 0 in for x again in the f prime, and we have something like this, which temporarily might cause us to be a little anxious because we have to think about, well, what's f prime of 0? That's a good question. You know, if you go to this graph and you think about, well, what is the derivative of that graph at 0? It might be a pretty tough thing to do, but it really doesn't matter, does it? Because we have this 0 alongside that's going to multiply and cause the result to be 0. So we can see that the two one-sided limits are the same, which does say that the limit of g prime as x approaches 0 from both sides does exist. We'll move on to step 2. Step 2, I think in our chart mentioned finding out or discovering whether or not g prime was defined at that particular value of x. So we think about, well, what's g prime of 0? And by virtue of this inequality symbol being underlined, that means that we are allowed to plug 0 into the function as long as it does provide something that makes a little bit of sense. And it turns out, kind of like what we did before, 0 times f prime of 0 comes to the forefront again, which gives us a 0. We see that everything here on the right side of the equal signs are all in alignment. So that means that the limit as x approaches 0 of our function g prime of x was indeed equivalent to the right side, which is also equivalent to the value of the function there. So all three ingredients of the definition of continuity at a point are satisfied. So we can finally say, well, therefore, yes, g prime of x, make sure you reference the right function, g prime of x is continuous. You can certainly abbreviate the word continuous at the point at x equals 0. So that takes care of our part A. I'm going to gloss over part B here. Part B, it reads somewhat similarly. It asks to show that g prime of x is differentiable. And that would involve you investigating, first of all, the derivative of g prime, and then doing that same sort of attack with those one-sided limits and using the definition of continuity there as well. Now, the reason why A and B are structured in this problem at the very beginning is because we're going to use those in a later problem that you're going to see in a moment. I'm going to also skip part C. I'm going to invite you to definitely take a look at this, sign up for homework. We'll have the key available here with a few hours at maybe this evening or tomorrow morning, and you can easily find and classify any local extrema for g of x on that interval -3 and 6. So it invokes another really powerful AB idea. But I would like to talk a little bit more in detail here about part D. We haven't talked about these special existent theorems a whole lot. They've kind of showed up here and then in some of the free response questions. But part D says the conditions for the mean value theorem are met for g prime of x over the interval -3 to 5. That's probably has a lot to do with part A and part B being the way that they are. Apply the mean value theorem over the integral -3 to 5, and in doing so, that will guarantee a value of C such that g double prime of C is -17/8. Our job is to use that information to figure out what the value of f prime of 5 is. So again, it's nice that we don't have to state the conditions of the mean value theorem, right? It says that they've already been met. So you don't have to say that we have this function g prime that's continuous. We have this function g prime that's differentiable. Those are already established. So what we will do is think back, well, what does this mean value theorem say? Well, it says that we've got this second derivative of g, this instantaneous rate of change, if you will, right? And we know that that's equivalent to -17/8. But by definition of the mean value theorem, that says that we would just simply take the average rate of change of the original function that was given. Now that original function is, once again, g prime. So you're sort of working on a different level of a derivative here. Normally when you apply the mean value theorem, it might be for a function f, and then you would take the average rate of change of f by subtracting a couple of f primes over some x's. Now this original function is g prime, and we're going to use g prime at 5 minus g prime at -3 as our numerator, and we'll divide that by 5 minus -3, and of course that's going to be equivalent to the derivative of g prime, which is g double prime. So all we need to do is correctly evaluate each of these particular function values. So g prime of 5, well, once again, 5 is going to take us to the second part, right? The interval from 0 to 6 is where 5 lives. And so we'll use xf prime, and we'll plug our 5 in there as such. And then we'll drop in our minus sign. And then g prime of -3, that is going to have us move up here now, where x is defined to be -3. And then that produces an f of -3. All right. And then, of course, our denominator is going to be 8. 5 minus -3. Let's simplify a little bit. 5 times f prime of 5. Well, f prime of 5, that bothers me a little bit. We really don't have the means by which to find f prime of 5. I mean, we're talking about this point right here and whatever his slope of the tangent line is, but we really don't have any way of figuring it out. And besides, isn't that what the question is asking anyway? So let's move over to the f of -3. So we can't do much with this, but we can find f of -3, and we just go to our graph, and you can see right up here that the y value at -3 for that function f, right, is going to be +2. All right, and we still have the denominator of 8. Now at this point, we just basically have to sort of equate this all the way back to the -17/8. And to save a little time here, we can see that the two denominators are both 8, right? So we can go ahead and cancel those just by multiplying both sides by an 8, let's say. And it's pretty academic from this point out. Just make sure that you get that negative sign in with that -17. So if we add 2, we're looking at -15, and then once we divide by 5, we have our -3, and that's the value of f of prime of 5 that we were looking for. Let's move on to part E. We told you that we were going to try to invoke some BC ideas, right? And here's our chance to do that with BC1. So we were asked here to evaluate the definite integral from 0 to 6 of g prime of x. Okay, seems pretty simple enough. Noting that the boundaries of integration span from 0 to 6 pretty much shines the spotlight on the bottom piece of that function. Remember, all these problems seem to revolve around this piecewise function g prime. So what I would suggest is that we go ahead and get a little clear look of what we're actually trying to integrate. G prime is nothing more than x times f prime of x. Okay, now when we take a step back and we start to think about all of the various integration techniques that we have at our disposal, our hope is that you see that this seems tailor-made to use an integration by parts. In fact, we've seen some problems kind of like this before that have that vibe to it. Again, your AP exam this year is not going to consist of integration problems that are going to be written in a very analytic way, right? You're going to see them disguised with function notation and things of that nature. And that's what you want to make sure that you're really on top of and that you can recognize. So in this particular case, I'm going to let u be my x. And I know I always set mine up just a little differently. I like to write my dv sort of on another line, a line below, only so that students can kind of understand the difference between differentiation and integrating. Differentiation is going down, right? Begins with the letter D. So we take the derivative of u and we get 1, or we can swing the dx over. And integration, boy, I wish integration started with u. That'd be cool, right? Up, but it's close enough. It's a vowel. So if we integrate dv, we get v. And that, of course, would just do away with the prime notation, and we have just f of x. And then we just remember that our formula is u times v starting with that first. So we'd go u times v, which is x times f of x. And of course, that's outside of the integral, so we can start evaluating our boundaries. And then we would subtract v du, which would be these two components, and that would also be housed in that original integration. So you have something like that. There's a variety of ways to structure your integration by parts. If you're doing something that's been very successful for you, there's probably no reason that you need to change. And of course, you could use a tabular method for this problem as well. So if we continue with this, we plug in our 6 and we get 6 times f of 6. And we'll subtract and we plug in our 0, which is 0 times f of 0. So we have that pretty much taken care of. And then we'll subtract. And then we see this integration of f of x that is very conceptual in nature, nothing really to integrate analytically. But we do remember that our good friend f of x was this graph up yonder, right? There's a Hoosier word for you, yonder. And integrating from 0 to 6 is just going to ask us to find the area between the curve and the x-axis. And we notice that we have a bit of area here that's going to span the region from 0 to 4, which I've just covered up, which is going to be 7. And then we have this area from 4 to 6 that finishes that particular interval of 3.5. However, signed area is going to be taken into consideration because this area is below the x-axis. So we're going to take the positive of that 7, and we're going to subtract the 3.5. Now notice I'm very careful about how I handle that, and that I put that in parentheses because it is a quantity that follows this minus sign. And then the only thing left to do is start evaluating. I'm going to have to maybe scroll just a little bit here, and I apologize for that, but we have to figure out this f of 6. So if I go back to the graph here, f of 6 looks like it's going to be this value of -3. So we'll use him. And then I have, well, 0 times f of 0. I don't really think we need to concern ourselves with what f of 0 is, as long as we know it's something that's continuous, and it is. And I think from the graph, you can tell it was equal to 0. And then 7 minus 3.5, of course, is going to be 3.5. So now you just have a -18 minus 3.5. You put those together, and your final answer could be -21.5. Of course, you would be fine stopping at any of those 3 locations because they are all in this final numeric form that are all equivalent. And I'm not going to talk about f other than just to kind of display it on the screen there for you to look at. But hey, what would a great BC question, what would a BC question be if it didn't have this Taylor polynomial connection to it? So Brian did a really good job of infusing that particular element into this BC1 question. And certainly we'd like you to try that on your own. I'm going to hand it off to my friend, Brian. BC2, what do you got to say about that?
Yeah, so I love that problem that Tony just did because it really does show you how we're connecting the idea from today, limits and continuity, to all of AB and then to BC as well. And so each one of these FRQs that we're doing, not just today, but this entire week, we're going to see a similar idea. So FRQs that start with the topic as well as other AB topics and then connecting them to BC topics. What a really good practice as you're getting ready for this year's exam. And so before we look at BC2, Tony, I did promise that I was going to show you a quick math trick. So I'm going to spend maybe 1.5 minutes showing you guys the math trick I showed Tony. And when we were in high school, Tony had lots of friends. We didn't know each other in high school. Tony, I think, was graduating high school when I was probably 1 year old, maybe. I don't know. Tony, were you like 70, 65? I don't know how old Tony is, but close to that. No, he's very young, but I like to tease him because he is a little bit older than me. But Tony had friends in high school. He was in a band and all kinds of sports. And I was the kid that stayed home and played with numbers, right? So I didn't have a lot of friends. Numbers were my friend, like par Erdish, right? And so I used to look for different patterns in numbers. And so one of the things I noticed in high school, I'm sure millions of other people have noticed it too. And this is not a new discovery, so don't think I created something new. And you might have seen this before, but I used to think about how can I square numbers like 96 squared, right? And so I look at 96 squared, and I know now that it's 9,216. And I didn't have that memorized. I just did it kind of in the moment. But I want to show you how we can square numbers that are close to 100 in your head instantly, essentially. If I did like 107 squared, for example, something like that, right? What's 107 squared? Well, I'm hoping it's 11,440. 49. And so how are we going to do that? Well, here's how we're going to do that. Let's say a number is close to 100, like 96. We'll go back to that example. Figure out how far from 100 is it, right? So 96, how far from 100 is it? Well, it's 4 away, right? That 4 is going to become a pretty important number because since this number is less than 100, it's not quite 100, we're going to take that 4 and we're going to go ahead and subtract 4 from 96. So however far away from 100 it is, let's subtract that. 96 minus 4 is 92. And then we're going to take that same 4 and we're now going to square it. And when you square 4, you get 16. And that's your answer right there. Seems kind of crazy, doesn't it? Well, let's see how it works with another example. What if we did something like 94 squared? It's also pretty close to 100. Remember, the first step is to figure out how far from 100 it is. So 94 is 6 away from 100. And 94 is less than 100. So we're going to take that number 6. We're going to go ahead and subtract it again from 94. So however far away from 100 it is, you're going to subtract that again. So 94 minus 6 is 88. And then you take that number. Remember how far it was? It was 6. We take that number and we square it. And those are going to be the last 2 digits. And so 94 squared is 8,836. Now, what about this 107 number? Because that was, again, it was close to 100, but now it was more than 100, right? So if I wanted to do something like 107 squared, the same rule applies. We're going to figure out how far from 100 it is. Well, 107 is still 7 away from 100, right? But it's over 100 instead of less than 100. The first 2 examples were less than 100, but what happens if the number is more than 100? Same idea, but instead of subtracting 7, we're going to add it. So if it's the number you're starting with is less than 100, you're going to subtract. If it's more than 100, you're going to add. So 107 plus 7 is 114. But then we take that number and we square it, right, for the n. 7 squared is 49. Now, I will mention, sometimes you have numbers, at the further away you come from 100, a little bit more tricky it is. But what if we did something like 97 squared? Okay, so 97 squared is 3 away from 100. Take 10 seconds and see if you can come up with the answer for that. And you can probably do it in your head, right? Or kind of jot it on paper, and we'll see whether you have picked up on this trick or not, right? So 97 is 3 away from 100. We're going to subtract 3 since 97 is less than 100. We're going to subtract less than, and we get 94. And then we have to square 3, and 3 squared is 9. So how do I handle that? Well, when you square the number, it really needs to be 2 digits no matter what. It's always the last 2 digits. So if it's just a 9, we can write that as 09 instead of just the number 9. And so 97 squared is 9,409. So there's the math trick for the day. I showed it to Tony. So now he has the best of both worlds. Now we had friends, music, sports, fun, and he has the things that I learned in high school, and I have just only this. But there's your math trick for the day. I'll show you a couple more. When I was in high school and college and as a teacher, I love studying numbers, love looking at numbers, and love to kind of figure out patterns. And so I think a couple, times a week we'll share a little bit of a math trick of how numbers work that maybe will impress your friends. If they don't impress your friends, then you got to find some cooler friends who will be impressed by this. We're moving on to BC2, and we're just going to look again at a couple of parts on this, not the whole question. We have a whole bunch of parts that we're not going to get to, but there's a couple of parts that I want to share to make sure that we are understanding how we can make these connections. So we have another piecewise function h, and h actually has 3 pieces this time. The top piece, notice h is defined by a function of h, which is going to be kind of an interesting part of this problem. The middle piece is this fraction that has some k value that we don't know. And the bottom piece is this rational function 12 over x squared. And part A says, find the value of k from that middle piece that makes h continuous at x equals 2. So notice that x equals 2, these are the 2 branches that we're concerned with. These are the 2 branches that are going to meet together when x is 2. And we talked about the first rule of continuity is, well, first of all, we're not checking to see if h is continuous, right? There's always, be really careful about the wording of the question. The one that Tony did and the one that I did originally was all about, is a function continuous at a value? We're not asking that. We're now asking you to find a value of k that would guarantee that it's continuous. So it's a little bit different setup, but the same idea applies, that if a function is continuous at 2, I need to guarantee that the limit from the left of h of x, in this case, is equal to the limit from the right. That's how we're going to make sure that our function is going to be continuous. Now we know we have other requirements, but that's going to be the first requirement, is the left and right hand limits. Well, the limit as x approaches 2 from the left would be utilizing this middle piece here. So if I go ahead and plug in 2 for x to this middle piece, we're going to get 2k minus 1 on top. If we plug in 2 into the bottom, we're going to get 1 times 4, or just 4. And then for the bottom piece, we're approaching 2 from the right-hand side. We're going to get 12 over 2 squared, or 12 over 4, which is 3. And so in order for this function to be continuous, this means that my two answers have to be the same, right? And so we have 2k minus 1 equals 3. And then now we're just solving this for k, and we can multiply by 4, and then add 1 and divide by 2, and we're going to get just a simple 13 over 2. So if k is 13 over 2, this function is going to be continuous. And we could verify that by checking the limits with k in there and checking the point, but it didn't need us to, just wants us to find the value of k that would guarantee that. So that's going to be our part A. And then I want to look at part B as well, because this question is a limit question. And it's a limit question. And whenever you see a limit question on a free response problem, your radar should go up and be thinking, this is probably going to be a L'Hopital's rule question. And so it doesn't have to be. We actually saw a question on last year's exam on the free response that was a limit problem, and it wasn't L'Hopital's rule. And a lot of students started doing L'Hopital's rule unnecessarily. But whenever you see a limit, that should be your your instinct, is it might be L'Hopital's rule. And this is a good question because it connects us to this idea of continuity, in the sense of, to show something's continuous, we had a very specific procedure we had to follow, because there's a definition involved. And in order to invoke a definition, you have to show all the pieces of it mathematically. The AP exam, one of their goals is to allow you as a student to think and to act like a mathematician. They want to give you opportunities to be mathematicians. And part of that is showing proper notation, invoking conditions, and invoking definitions and theorems properly. And so L'Hopital's rule is a theorem. We call it L'Hopital's rule, but it's really a theorem because it's an if-then statement, right? And so how you write this is going to be really important. So pay really close attention to this. And Tony and I will bring this back up again in the next coming weeks as well, multiple times, because it's one of those areas that seems to be tested on every FRQ or every year, now, but yet students don't quite know the proper notation. And so to do L'Hopital's rule, we really have to evaluate the limit of the numerator. This would be h, not f, right? The limit of the numerator and the limit of the denominator separately. So we have to take the limit as x approaches -3 of the numerator, and we have to take the limit as x approaches -3 of the denominator. A big mistake that students make is they kind of just write things like equals 0 over 0, right? That's a big no-no. You can't equal 0 over 0. L'Hopital's theorem actually tells you to evaluate these two limits separately. And if they're both 0 or both infinity or negative infinity, then we can invoke L'Hopital's theorem, but we have to show them separately. So it's really important that we show them distinct like this. And so the limit as x approaches -3 of h is going to be h of -3 minus 4. And now I got to go find out what h of -3 is. Well, I'm going to plug it into the top piece because that's the one that's going to include when x is -3. Well, notice the top piece is just another function, isn't it? And so h of -3 is just 3 times h. If I plug -3 into here, -3 squared minus 6 just becomes 3. So really, we're kind of jumping around because h of -3 is going to be 3 times h of 3. And to find h of 3, now I got to come down to here when x is greater than 2. So it's going to be 3 times, if I plug in 3 into here, it's going to be 12 over 9 minus 4. And if we reduce all of this, guess what? We do get our 0. And the limit of the denominator as x approaches -3 is just going to be 9 minus 9, which is 0. So notice how I showed those two limits separately. That's going to be the first step to even have a chance to invoke L'Hopital's theorem is by doing those limits separately and not writing just equals 0 over 0 or arrow. This is the proper way of showing it and how you communicate that. So now that we both get 0, we know we can apply L'Hopital's theorem. So now I can just say by L'Hopital's, and then we know L'Hopital's theorem says we can just differentiate the numerator and the denominator, that the limit of this function is going to be equal to the limit of the derivative of the numerator over the derivative of the denominator. So h prime over 2x. And in this case, I know if I plug in -3 to the bottom, we're going to get -6. So all I have to be able to do now is find h prime of -3, right? And so now it requires me to have h prime. And we're given a function of h. So we're going to have to do a little bit of side work here to figure out what is h prime of x. I can't figure out h prime of -3 without first knowing h prime of x. And so if I take the derivative of these first piece here, it's going to be 3 times h prime of x squared minus 6 times, by the chain rule, 2x. And that's going to be for values that are less than -2. I'm going to get rid of the equal sign because I don't know if it's differentiable there or not. But this is going to be a nice chain rule derivative. The middle piece, I'm going to leave out for now. And the reason why I'm going to leave it out is because it turns out we're not going to need it for this problem. But if we had asked you to find h prime of x, we would solve all of that. And then I also need to find the derivative of this bottom piece. And to find the bottom piece's derivative, I'm going to bring that x squared up and make it -2 first. And so this derivative is going to be, what is that? -24 x to the -3, or x cubed. And that's going to be when x is greater than 2. And again, I'm going to leave off the equal sign because I don't know if this function is differentiable at those corner points or not. And so if I want to find h prime of -3, I'm going to plug it into the derivative up here at -3. And that's going to give me 3 times h prime. If I plug in -3 for x, again, we get 9 minus 6 in there, which is going to be just a 3 times 2 times x. Remember, x was -3. And so that's going to be times -6 all over -6. So now the nice thing is the -6's are going to cancel. And all we get is 3 times h prime of 3. And now we got to find h prime of 3. This problem has us bouncing back and forth between these two limits, or these two pieces of this function, quite often. But h prime of 3 is now the bottom function, right? And so it's going to be 3 times h prime of 3 is right here. And so that's going to be -24 over 3 to the third power, or 27. Since this is an FRQ problem, we're allowed to leave it, right? We don't have to simplify our answers. We can leave it like this. But if you wanted to simplify it, I think all of this just becomes what? -24 over 9, which is going to be -8 thirds. So the final answer, if you did reduce it, would be -8 thirds. Pay more attention to how we set up L'Hopital's theorem, and knowing the notation, showing the left limit and right limit separately before you apply L'Hopital's theorem. And don't get too focused on the fact that we had this kind of crazy piecewise function that had us bouncing back and forth. That's kind of the top of the difficulty scale of what you might see for L'Hopital's theorem. But Tony and I will give you more examples of these in the coming days and weeks. That way you can keep practicing this proper notation for doing this. So there's a lot more great problems on here, but I'm going to leave it at this one. And then if Tony was going to kind of make a mention, I think, of BC3, and I don't know if I'll have time to get through any examples or not, but he might point out a couple things for you guys to try at home.
Certainly, BC3 has a lot of really wonderful elements. As you move through it, you'll see that Part A mentions about continuity. Very similar to what we did before, but the big key element that's different is the fact that you've got a table of values. So you're going to attack a lot of the same concepts, but in a different environment. And we will say that L'Hopital's rule makes another prominent appearance with this particular problem. And towards the end of it, it looks like you may be doing some U substitution integration. So we certainly invite you to take a look at problem 3. It is the last of the free response questions. But it does have a lot of parts to it. These problems have a pretty robust nature to them as they go up to part D, E, and F. So we certainly would love for you guys to take a look at those. So Let's tweet out. Yeah, let's tweets with Tony here. So what do we got going on here with our AP Teachers Rock hashtag? Well, we're going to recognize the fact that AP Teachers Rock, shout out to my BC teacher, Mrs. Hansberry from Little Rock Central High School. She worked so hard to prepare us for the AP exam, and she teaches us wonderful calculus. So congratulations to you, Miss Hansberry. And for our AP Students Rock, special message here. I am so proud of how all of my students are working and helping each other. TJ even helped me navigate YouTube to find some attachments. So we want to thank Mrs. McGreevy from Spencerport High School, just outside of Rochester, upstate New York, right along Lake Ontario. So thank you very much for that. Go Rangers. And I also want to recognize a young lady who's become a friend of ours, Lydia. Lydia, thank you so much for the wonderful message over the weekend. Lydia is a student who attends the Rift Valley Academy. It's in Kijabe, Kenya. It's a school there in the eastern part of the continent of Africa. And due to the coronavirus outbreak, she has had to quarantine herself all the way into northern Africa. So she's in Tunisia right now. And Lydia, we just want to send out our thoughts and prayers to you, your family, and of course, all of the other students at Rift Valley Academy, and wish them much luck in preparing for their AP exam. And this truly is a global effort. We have students watching and joining us and learning with us from all over the world, and we're so excited for that very fact. Once again, the lessons for the upcoming week, all connecting AB to BC. So there you go. If you want to take a real quick peek at that, tomorrow we'll be back on talking about differentiation and integration, and we'll move into some other various topics throughout this week. And then that sets up next week for our problems type week that we'll talk about a little bit later. So again, if you're having trouble with internet access, with equipment access, you can certainly have yourself or a friend of yours reach out to cb.org/tech to get a lot of those issues remedied. And Brian, I think that takes care of us today. It was a great show. Thank you so much for your math magic trick. I thought that was witchcraft at first, but it's a wonderful little tool. And hey, maybe we don't need calculators as much as we think, right?
Exactly. And Tony, real quick before you head us out here, stay tuned, students and teachers. This coming week and next week, we got some more math tricks coming your way. And I believe Tony even has, I won't give it away, but a guest speaker that is going to be, you should recognize this guest speaker and be pretty excited about it. So stay tuned to that. And I want to echo Tony's sentiments of Lydia, but we get so many really cool tweets, emails, and messages from students and teachers, and we cannot quantify how much we appreciate all of the support. And there's a lot of gratitude and a lot of camaraderie, and we're all coming in this together. And we're so excited and grateful that we're a small part of this as you're preparing for the exam in this very unique situation that we find ourselves in. So thank you guys and girls for all of the amazing just emails and notes of support. Tony and I know we appreciate them, and we're saving them because that's what keeps us going on those nights that we're working until 3 o'clock in the morning trying to prepare for these lessons pretty much every day.
That's right. All right, till next time, stay safe, stay healthy, and keep learning.
AP Calc, yes, AP Calc. Welcome you to